How's everybody doing?
Pretty good.
Good. How was the weekend?
It was too fast.
That's always that's always the case, isn't it? Oh, I forgot to do that. Well. I am going to pop off the meeting here for about 15 seconds because I forgot to switch my Surface screen around and I need the keyboard. I forget that I'm teaching with Excel. So bear with me for a second. Maybe. There it goes. Here we go. Oh, goodness. There we go. I think I'm back. Yep. Oh, I hear people. I think I'm back now, yes. Sorry about that. I forgot to switch my screen. I bought a new Surface because the other one was giving me fits, and I bought basically what Ashlyn has, but I forgot I was writing for the other two classes. And of course, in this class, I want to type in Excel, and I didn't have my keyboard, so I needed to flip it back around. And well, whatever. I had to disconnect to be able to reconnect, is the end of the moral of that story. My apologies. Any questions at all over anything before we get started? All right, I wanted to do another example.
Alright, Joe, you're kind of a robot right now.
Well, there's a surprise. My internet has been giving me fits all weekend, and then of course I just made it mad by disconnecting. So, am I better? Am I audible? Oh no, it kicked me off. Shoot. I think I'm back again.
Yes.
Yes.
Yeah,
Yeah, I hear you now.
Okay. Sorry.
you turned into like a robot.
Well, and then it kicked me off. So, yeah, this is what the internet has been doing to me all weekend. It's been behaving itself this morning so far, but
Yeah,
apparently,
your voice keeps cutting it.
well, yep, so did yours.
Yeah, I don't think this is gonna be a good class day.
Yeah, well, let's give it a few more minutes, and if it really sucks, I'll just record and let you listen to it later.
Okay.
All right, let's see what happens. I'll try again. Was there any questions before I start?
I actually had a question from the video.
Oh,
I was wondering if you could explain a little bit about using the full unit for the p-value.
sure, I can do that. So when you're, let me explain. Can I explain that when I get to it? Would that be okay?
Yeah,
Okay,
yeah.
cool. But I will definitely explain about why we use the full unit as opposed to a half. I can do that. Was the stuff with the confidence intervals we talked about last time okay, or should I do one more example?
Should do one example.
I should do one
because it's been a week now.
Yeah, it's true. It's been a week and it's on the screen, so I was already preparing on doing one. All right. So this one has water softener pellets, and it wants to construct an approximately 95% confidence interval for the median. So remember that when we're trying to construct the confidence intervals for these different things, we want to try to be at least as symmetric as possible around the percentile that we're trying to construct the confidence interval for. So in general, when you do your percentiles, you can figure out the position of a percentile by doing that n+1 times the probability that you're interested in for the percentile. So for the median, of course, if I did the n+1, which is the 15, because there's 14 things here, and the probability for the median would be 0.5, the position of the median should be 7.5, which makes sense because you're splitting 14 things lined up so that half are below and half are above the middle point. So it better be 7.5. So we're looking for this particular percentage of confidence interval that's also symmetric around the 7.5. So it could be 7 to 8. It could be 6 to 9. If I could type. It could be 5 to 10, 4 to 11, and so on down the line. So, if you wanted to figure out what these the probabilities were, so if you wanted to figure out what the probabilities were, you can go back to the binomial distribution range command here. And the number of trials that we would have, well, in this case, we've got 14 trials total. The probability of success is 0.5. The number that we're looking for, the low end, is this A13, and then the high end would be a B13, So what I did this computation for, again, is this would be the probability that we had, or between, or at least 7 of them are below the median value, but at most 7, so it's exactly 7 essentially in this case. But we're doing the range between these two so that we can figure out what the probability distribution would be. You know what? I need to change the number a little bit. So this should be, I think I need to do -1 here, the way I have this. There we go. Okay. So remember, when we're doing the confidence intervals, it's at most this many, or excuse me, at least this many are below the median value, and then it's at most 1 less than this value. So that was what I messed up when I typed in the formula to start with. The reason why I'm doing this is to get that confidence level that I need, so I figure out where the bounds are. Because it's asking me for this 94.26% confidence interval. So that's why I wanted to know, okay, if I use 7 and 8 for my confidence interval, what's the probability that my median is in between the 7th and the 8th ranked number, try that again, 7th and 8th ranked data values in my sample. So when I do this binomial distribution range one, remember, I want at least this many and at most this many -1. That's why I had to subtract the 1 off of here. And then I just copied it down so that I could get to whatever number they were asking me about here, this 94.26. So what this tells me is that I want to pull out the 4th order statistic and the 11th, is what this is telling me. So to get to that, I'll go back up here, and I'll use that rank average command, this one here. I want to rank each individual data point in accordance with the data set that it comes from. And I want to do it in ascending order. So I'll type in a 1. So this will give me whatever rank the data point is relative to the whole set, and I'm going to do from smallest to biggest. And then I'll just make this the same size as what the data set is. So when it does the rank average command, when it has 2 that ties, it takes the 2 ranks and averages them together. So notice that we want 4 and 11. Well, the upper level would be the 11 then. So the upper one is the 80.51. That would be the 11th one. The 4th one, well, notice that the 4th and the 5th are the same. That's why we have 4.5 on each of these. So the lower bound, it doesn't matter which one you use. You're going to use the 80.28. So this 80.28 to 80.51 will be your bounds for your confidence interval for the median of the distribution. Does that make sense?
Yes.
Yeah. Okay. See? Good. Okay. So Part B says that we could use the interval from the 6th order statistic to the 12th order statistic as a confidence interval for 0.6. So just to see where the 60th percentile should be, again, I would take n plus 1, which is the 15, times the probability, which is 0.6. So 9 would be the where it would be the position of the 60th percentile. So again, symmetric around that would be 8 and 10, 7 and 11. I don't need to really write these down, but 6 and 12, that's where they're getting the 6 and the 12 from because it's symmetric around the 9. If we want the confidence coefficient for the 6 and the 12, we would do the same thing that we did before. I'm just going to copy the exact same cell down because it's the same formula with the same references. So if I want the confidence coefficient, except I do need to change the probability here. Instead of 0.5, I need this to be 0.6 because it's the 60th percentile. So we need at least 6 of them to be less than, and at most 11 of them to be less than. So that's why I'm using the 6 and the 11. I got to change the probability to 0.6 because we're looking for the 60th percentile. So the probability that you're below is 0.6, 60%. And you get a confidence coefficient of about 90%, 90.19. But again, the way I'm getting that confidence coefficient is using a binomial distribution on the number of trials is 14, and the probability of success in this case is the 0.6. It's matching the percentile. We need at least the lower number and at most one less than the higher number to be less than the 0.6. Because remember, we're trying to get that 60th percentile to be between two things. So the last one, the one that's on the right, has to be above it. That's why I'm using one less here. And so then again, if we pull these out, if we want the confidence interval, the 6th one is the 80.32, just reading it off my table here. And the 12th one is the 80.53. And that would give you an approximate 90% confidence interval for the 60th percentile. Any questions on that? Okay. Well, let's go on to the new stuff, which is the sign test, the sign rank tests, or the Wilcoxon tests, the Wilcoxon sign rank test. So let's just talk about the sign test first. So the sign test is just a way to make a test for the medians. So in this particular problem that I have, we've got the median of the set of data points that they give you. Apparently it's a 1 pound bag of carrots. And they want to test whether or not the median is greater than the 1.14. All right. So if all we're doing is a sign test, we want to basically count the number of these that are actually above the 1.14. That's all we're going to count. We're not going to take into account any magnitudes of how far things are from the median. All we're going to do is count how many of them are above the 1.14, which I might as well just use Excel to do that. So if I use the count if, here's my range, and I want to know out of that range, are we greater than the 1.14? So in this case, it says that 9 of them out of the 14 are greater than the 1.14. That's all I did there. So is that enough evidence to conclude that the median probably is above the 1.14? Well, we can do this by using the binomial distribution again. We've got, I'm going to need to do 1 minus because I have to go greater than this. I want to know what the probability is that we had 9 or greater. So the number we're interested in is, if I want 9 or greater and I want the cumulative probability part, I'm going to need to do this minus 1, because this will give me the probability that it's 8 or less out of 14 trials. The probability of success, since we're dealing with the median again, is 0.5. And I want true. So all this computation is doing is, if the median were in fact 1.14, what's the probability that I would get 9 data points out of the 14, or excuse me, at least 9 of the data points out of the 14 to be above the 1.14. Okay. The reason why I have to do 1 minus here is because we're going above the 1.14. So I've got the binomial distribution command will calculate from 0 up to a number. That's why I had to do 1 minus. All right, so the probability this happens is actually 0.2. Where you have a level of confidence here of 0.1, a significance level of 0.1, so we would not reject in this case.
Why are we not rejecting?
Because my p-value is not low enough. This represents the p-value here.
Okay.
Yeah, it's bigger than, yep. If we went the other way and wanted to figure out a critical region, I would need to know at least how many have to be bigger. And I think in this case, if I do, let's see here. Say if I do 9 and 14 and 0.5 and true. Yeah, so I would need, according to this, I would need 10 or more. The critical region would be above the 1.14. So the way I got this was...
You just lagged.
Oh, did I lag?
A whole bunch.
Oh, great.
So I have no idea what just happened.
Okay, cool. All right. So what I was doing here was trying to figure out what the critical region would be. Oh, well, never mind. Well, good thing I'm recording this so that I can take a intermission break here. Hi. I think I'm back. Am I back?
Yeah, you're kind of back, but you still sound like a robot sometimes.
Shocking. All right. Let me go back.
You started talking about like how to find the critical region, and then you just kind of like
I disappeared. Yeah.
Yeah.
Yeah, cool.
It was a pretty cool magic trick. But...
Poof. There we go. Yeah, all right. So let's go back to the critical region. Okay, so I need to know at what point it becomes unlikely to see a certain number of the data points above what I think the median is. So when I did this one, I looked at what's the probability that we would have 10 or more above the 1.14. So I did the complement of 9 or less. That's what this computation is doing here. And got 0.09. So that's below the 0.1. So that's why I would use 10 or more would be the critical region. So it was just one short of being able to reject. So that's what the second computation was. The second computation was figuring out what the critical region would be. The first computation was actually just the p-value associated with this particular test statistic that we got. That was what I was trying to do.
So why did you use, in your critical region, why did you use the 9 for your...
For this part? So the reason... okay. So the reason why I put 9 here was because remember that this command, the binomial distribution command, goes from 0 up to a number. And we want to do the complement of that. So... to get 10 or more, I have to do 9 or less and do 1 minus. That's why.
Oh.
Does that make sense?
So then how did we...
Oh.
Why did we know we wanted 10 or more?
We didn't. I was trying to figure out what the critical region would be according to this value here. So it was going to be more trial and error. I just happened to hit it on the first try.
Oh, okay.
Because if that one didn't work, I was going to have to change the 9 to a 10 and see if it was better.
I see.
Because notice if this would have been 0.05, then 10 wouldn't have worked because I'm at 0.08. So I would have had to have done, if I wanted 0.05 rather than 0.1, I'd probably have to make this a 10. And so then that would be 11 at that point. Does that make sense?
Yeah.
Okay. I mean, it's not unlike what I was doing over here. This was trial and error as well because I don't know where I don't know off the top of my head where this confidence level is. So I had to go through and compute it until I hit the one that they wanted. All right. So far, so good? Or am I roboting again? All right.
A little bit. You're cutting off some, but...
Okay. Of course I am. All right. So, with the Wilcoxon statistic, though, we start to take into account magnitude of how far something away is from the median. To try to introduce that into the likelihood that the median is a certain value. So, kind of what I mentioned on the video, if we look at the numbers here in this example, notice that the ones that are below the 1.14 are close, right? 1.12, 1.13, 1.06, 1.12. Those are relatively close to the 1.14. Really, the only one that's not that close is the 1.06. The rest are 1.11, 12, 13. Versus the ones that are above, you got a couple of that are relatively speaking, much farther away. You've got a 1.23 over here, a 2.9, a 2.5, a 3.1, another 2.3. On a relative scale, those are farther away from the 1.14 than the other ones are below. So even though we didn't reject with a sign test, looking at the actual individual values, it looks like we really should probably look at another way to test this to see if we're going to reject or not. So that's what the Wilcoxon rank test does. So what we're going to do is we're going to rank them by magnitude of how far away they are from the median, the purported median. So the first thing I'm going to do is I'm going to subtract the median from each of these. So I'm going to take the 1.14 and subtract it from each of these. Okay, so I want to rank these by their signs and then put the signs on there. So, well, I want to rank them by their magnitudes, I mean, and then put their signs on there. So I want to, let's also do, well, actually what I probably should have done to start with is take the absolute value of that, because I want to rank them by their magnitudes here. So I'm going to take the absolute, because I don't want to worry about the sign to start with. I want to know how far each individual point is from the median as a distance idea and nothing else. So what these values are in the 10 and 11 rows here is just how far each individual point is from the median, the purported median of 1.14. Then we're going to rank them. That's really weird feedback I'm getting. People still able to hear me?
Yeah.
Yeah? Because I was getting robot voices coming back at me and I wasn't talking. That was weird. Okay. All right. So, get off of there. So the first thing I want to do is I want to do the rank average of each individual point relative to, or each individual magnitude relative to the rest of the magnitudes. And I want to put it in ascending order. So that's important to put the default, if you don't put a number in here at the end, is descending. We want ascending order because we want things that are farther away to be weighted more than things that are closer. So we want to make sure we put this in ascending order, not descending order. And if there's a tie, it's so weird. They start, if you read through the text, it says, we're assuming we have continuous distributions. So the likelihood that two end up at the same point are 0. And then they, in the homework problems, they give you a bunch where they have ties, which is just weird. But at least I think it's weird because they say the probability that you have 2 points should be 0, and then they give you all sorts of examples where they tie. It doesn't matter if they tie, just leave it as a tie, and you'll just sign it like you would otherwise. So just leave it as 2.5 and 10.5 in this case, is what I'm saying. All right, so before we calculate our test statistic, we need to put signs on all of these. So I want to, so for example, this 2.5 that's here, I want to make it negative. But this 7 that's here, I want to keep it positive. So the easiest way to sign this, at least what I think is, I'm going to take the number that's in the magnitude that's there, and I'm going to multiply it by the, well, it's the signum function, if you will. It's the sign command, the sign function of the thing that is signed. So what this SIGN function does is it puts a positive 1 if it's positive, it puts a negative 1 if it's negative, which is exactly what I want. And so all this is going to do is sign the ranks. All right, so then for your Wilcoxon statistic, which the book refers to as W, and in the video it looks like I just switched from a V to a W because the book, I was just following along with the book with the development. The Wilcoxon statistic is your sum of these signed ranks, which in this case is 67. All right, so the idea here is, okay, well, how bad is 67? I mean, that's a number, but we don't know how bad that 67 is relative to whether or not we should be rejecting the idea that the median is 1.14. So in the development in the video, we talked about how this W is the sum of independent random variables. And these independent, so for the independent random variables, the only values that can possibly come out are the positive rank or the negative rank, and each of them should have a probability of a half happening. Well, when you add those two together, the expected value is 0. So if I add up all of the ranks, the signed ranks, I should expect on average to get 0 if the median is true. So the mean is 0. And then if that's the case, when we do a variance of an individual rank, well, remember when you do your variance, you do expected value of the variable squared. Well, if I square I or square negative I get I squared. Both of them happen half the time, so the expected value for an particular one is just I squared. When you sum up all of the I squareds, you get that formula n times n plus 1 times 2n plus 1. Pardon me. So we have a mean of 0 and a variance formula that we can calculate. So we can, and then we also know that the bigger the n gets, the more and more normal this gets. That's a extension of the central limit theorem. It's not exactly the central limit theorem, but there's an extension of it that works. So basically, we can do a z-score for this, or do what I did in the video, but I'm going to do the z-score here just because it's just as easy. So I'm going to take the sum here, the 67, and I'm going to divide it by the square root of, there are 14 sample points, so it'll be 14 times 15 times 29. That's the n times n plus 1 times 2n plus 1 divided by 6. Because the n times n plus 1 times 2n plus 1 over 6 is your formula for the variance, and I'm taking the square root. So what I'm calculating here is a z-score. So the z-score is 2.1. And we know for a normal distribution with an alpha value of 0.1, your critical value would be like 1.28. So if I do normal distribution inverse, and of course I did, I can still do it this way, 0.1. This gave me the negative 1.28. I would, since I'm going greater, I would go the other way. So 1.28 would be your critical value, the absolute value of this number, since I'm going to the right instead of the left. So notice the z-score for this 67 is well above the critical value, so we would definitely reject here because of our z-score being that high. So notice in the sign test that we did before, we didn't have enough of them to be above the median in a binomial sense to be able to reject, even at the 0.1 level. But notice that this we would have rejected even at the 0.05 level, because that's definitely greater than the 1.96 that we usually, or excuse me, the 1.645 that we usually use for the 0.05 level. So far, so good? We okay with that?
Yeah.
Yeah. Okay.
How did you calculate the z-score again? What formula did you use?
I just did the test statistic that we found. So the 67. Okay. So we're just doing. Oops, that's the right one. So we're doing the regular old z-score formula that we use, where you do data point minus mean over standard deviation. So this was your data point. That was our test statistic. That's what's up in B19. The mean of the distribution 0, so I don't need to subtract anything off. So that's why I didn't put anything here. And then this is the square root of the variance. So for the W statistic, the mean is 0, and the variance is that n times n plus 1 times 2n plus 1 over 6, where your n is the number of data points. So that's where this 14 times 15 times 29 over 6 came from. Was from this variance formula here. And then I have to do the square root because I got to make it a standard deviation when I calculate the z-score. Does that make sense?
Yes.
Okay.
Thank you.
Yep, you're welcome. Okay. So, oh goodness. So, when we have to do, one of the things that I mentioned with calculating a p-value is that you have to do a continuity correction based on the fact that we've got all of these little rectangles from your probability histogram that tend to be under or over an individual the normal distribution curve. Either it's missing some area under the normal distribution, or it's outside of the normal distribution and it's gaining some area. Let me see if I can pull up the picture that I made for this. I know I haven't shared the screen yet. All right, so this is the picture that I made for the example that I did in the video. So in particular, if you notice on this, let's see if I can zoom in a little bit. Oh, stop it. Maybe I can zoom. There we go. All right, so notice on this rectangle that's right here, hopefully you can see the grid that I'm talking about. Notice that this rectangle goes across 2 units rather than 1 when we're doing this probability part. The reason why we've got it drawn this particular way, besides the fact trying to illustrate that we're going to do a continuity correction for 1 unit rather than a half, the reason why it's drawn this way, in this particular example, when you do the sums of these things, assuming that you don't have these half issues, which you shouldn't, because the way that you develop the theory is that you're assuming you have a continuous distribution, so the probability that you select 2 of them that have the exact same value is 0. Assuming that you have no halves, so you're using an integer value each time, when you add up these integer values, you're either going to get an even number as a possibility for every single possibility, or you're going to get an odd number as a possibility for every single possibility. So to give you an example of what I mean, if you only had 5 ranks that you were doing, the middle number, if you had 5 ranks that you were doing, the middle number is a 3, which is odd. And then the other ranks that you would have match up as either 2 evens or 2 odds when you add them together. So when you sum up 2 evens, you get an even, or 2 odds, you get an even. Bunch of evens together give you an even, plus that last rank that's in the middle was an odd. You'll always get an odd number, whether or not it's positive or negative that you're using for the signs. So if you only have integer values, you're either, no matter what the signs are, either always going to get an odd number for a particular statistic, or you're always going to get an even number for a particular statistic. So what that means is that in this example that I did in the video, there were 13 possibilities. The middle number was a 7, which was odd. Everything else will pair as either two evens or two odds when you add them together. So the rest of the sums altogether will be even, plus an odd in the middle will always give you an odd number. The possibilities you can get out are between negative 91 and 91, I believe, in that particular example. But in general, again, you can only get negative 91 to 91 odds. You can't get anything for evens. So when we're doing the probabilities, they actually go across a whole 2-unit interval rather than a 1-unit interval. So anytime that something's sticking out here above the normal distribution or is below the normal distribution, we're trying to smooth out that. We need to do that continuity correction for a whole unit rather than a half unit, because the halfway in these rectangles are all units now and not half units. So that's why the continuity correction has to be a whole unit rather than a single unit, or a half unit, I mean. Does that make a little bit more sense with that, Morgan?
Yeah, I did have one question though.
Sure.
Follow up.
Mhm.
So when you say, so we're looking at the ordered statistics, so like the place, when you say like, for example, when you said like the 7
Yes.
was in the middle.
Right.
Okay, so then what is the 91? Like, is that...
So if I say all your ranks were positive out of the 13, if all of them were positive, then the sum from the integers from 1 to 13 is 91.
Oh, okay. I see.
And then so that's one of the worst case scenarios. If they're all positive, that's as big as it can get. If they're all negative, then the negative of that is as small as it can get. So that's why I knew it was between negative 91 and 91.
Okay, thank you.
Yep, you're welcome. All right, so to that end, let's go back to my Excel. So the last thing it asks you for, what is the p-value? Now, honestly, if you have a computer algebra system, you could actually figure out the exact p-value of your test. The thing that I mentioned in the video about, what the moment generating function is, you can use a computer algebra system to expand out your moment generating function and pick off the coefficients that would correspond to being too big in this case. I'm never going to ask you to do that. I'm just saying that if you really wanted to do that, you could. It was an interesting problem for me to solve the other day. I mean, trying to get that picture to come up, by the way, that I did, that was about a 30-minute job for me to figure out how to get that to work. It wasn't something that was just built in. So anyway, to figure out the p-value in this test, we're going to the right. So we want to know the probability that this is bigger than what we would expect. So we need to do the probability that we are 67 or higher, but we have to do that unit correction and make sure we catch 67 with the unit correction. So we want to calculate for the p-value, we're going to calculate the probability that W is greater than or equal to 66 rather than the 67. And again, the reason why we use the 66 is because we want to make sure we catch 67 on the way up. All right, so how do we do this? We're going to use the normal approximation. This, we already calculated the z-score up here. That 2.1 is our z-score. So all we need to do is do 1 minus, because we want to go 2.1 or high. Oh, no, I calculated the z-score for 67. Sorry, I don't want to do that. I want to use the same formula. I do want to use the same formula here, but I want to subtract off 1. the reason I want to subtract off 1 here is I want the z-score associated with 66, not 67. So I want to do the normal I want to do 1 minus the normal distribution, standard normal distribution of this z-score, and then true. Okay, so let me just go through and explain this again, since I did lots of moving of the mouse all at the same time. To calculate the approximate p-value, I'm using the normal approximation for this particular random variable. To be able to use the normal approximation, I've got to do a unit correction because of the way that discrete random variable is working, and trying to use a continuous random variable to approximate it. And again, the reason why we have to use a whole unit rather than a half unit like we did before is because these rectangles are going over 2-unit interval for a base rather than a 1-unit interval. So that's why I'm using 66 rather than 67, because I want to catch 67 on the right tail. So I have to use 1 less so I can catch 67 on the way up. To make that a 66, that's why I've got the -1 here in my numerator. And all this is, again, for this computation here from this part, is a z-score. That's all this is. It's data point, which in this case is 66, minus the mean, which is 0, over the standard deviation. So that's all this highlighted portion here is a z-score. The normal that since we're using a standard normal, since we're using a z-score, it is the standard normal. That's why I've got normal.s here. Cumulative distribution, I want the cumulative part because I want to make sure I have accumulated probability. But this returns a left tail value, so I'm doing 1 minus to get the right tail value since we're going up. So your approximate p-value here is about 0.02. 0.019. Does that make sense with everybody? Is that okay?
Yeah, that makes sense.
Yeah, we okay with that? All right, we'll do more examples of this on Wednesday. I've got 4 more in here that I would like to do, and I got through 1. So we will definitely do more of these on Wednesday. I will also give you an assignment on Wednesday that'll be over the stuff that we've done in Chapter 8. And then my plan is to give a test over Chapter 8 stuff. The Chapter 8, the stuff that we're going to go to past Chapter 8, it's more conceptual, and the difficulty level ramps up significantly for the stuff at the end. So I want to give a test just over this stuff that's in the Chapter 8 stuff that we've done, that I personally think the material, since you're doing more computational things on Excel, I think it's an easier thing to get tested on for a test than putting in some of the other computational stuff that is, the more conceptual stuff that's more of the theoretical framework for being able to do hypothesis testing than it is that it doesn't really go with this stuff that it's actually just doing the hypothesis testing. So that's why that's why it seems like I'm giving you back-to-back tests rather quickly, but it's because of the way the material is breaking up and what I perceive to be the relative difficulty level on it. And I'd rather give you another test on stuff that is less difficult, I would say, than going right to the hard stuff and giving you a test on that and then giving you a final test on hard stuff. So that's the way I'm going to try to break it up, if that makes sense. Any other questions at all?
Yes, it is.
All right. We good?
Yep.
Yep. All right.
Yep.
Okay. All right. Well, I'll talk to you all later.
Okay,
All right.
thank you.
Yep. Have a good one. Bye.